Okay, so new section to talk about today, section 5.5. By the way, this is a big one. This is going to take probably 3 class meetings to make it all the way through. It's just a lot of stuff. It might be more than 3, I don't know. So anyway, change of variables is the big heading, and then this book attaches several sort of like applications and variations on change of variables, all in this one same section. A lot of books would break it up into at least 2. So anyway, here we go. The way we're going to do this, a lot like the way we do a lot of things in this class, I'm going to get to the multivariable idea by revisiting a single variable calculus concept, taking a certain very specific point of view on the single variable concept for maximum convenience of just extending upward into the multivariable. So here we go. The single variable idea we're going to talk about is the substitution rule. And now I know you all have all seen substitutions back in Calc 1 probably, maybe Calc 2, depending. Here it is. And so I hope that looks familiar. Point of view I want to take on this, a lot of people think of this as kind of an algebraic thing, like, oh yeah, well, you know, if you see this, then you can algebra and stick this algebra into there, and algebraically you get an answer. And there's nothing really wrong with that. But I want to view this a little bit more geometrically. Specifically, when we say x is g of t, I want to think of this literally as a function g, with its domain being the t-axis and its target being the x-axis. I want to think of this as something we draw pictures of, like this. Okay. So all right. Well, with this in mind, a point on the t-axis has as its image a point on the x-axis. Analogously, an interval on the t-axis has as its image, well, if you just plug in all these points and see where they go to, it has as its image a interval on the x-axis. And all of this is sort of exactly as you would think, probably. Okay, so now I want to, with this picture as our, framework for talking about this, I want to talk about 2 specific aspects of the substitution rule. The first thing I want to talk about is what I'm going to call the viewing this as a pullback. So what do I mean by a pullback? While points go forward, right? If you have a point on the t-axis, that has as its image a point on the x. It goes the same direction the function goes. Expressions, I claim, go the other direction. It's a little counterintuitive until I show you the following example that I think is pretty persuasive. Let's suppose I have a function like this, and I'm going to say that x is, and I'm just going to make something up here, t cubed plus t. Let's just say. It doesn't really matter. Let's just say. Okay. Well, what would I do with the expression cosine of t? Can I rewrite that in terms of x? No, I don't really see how immediately. Right? I'd need to plug in for what t is, and I don't have a formula for t, so I'm kind of dead in the water. So I can't really do anything there. But notice, if I have an expression, let's say tan of x, this is really easy to plug in because, well, I've got a formula for x right there. Right? X is just t cubed plus t. And so tan of x just turns into tan of t cubed plus t. Right? So again, what this function g, so this is our function g here, g takes points this way. But expressions, when you do the act of plugging in, expressions go the other way. This is, we call this pulling back. Points push forward, expressions pull back. Does everybody see what I'm talking about? This is just, diagrammatically, this is what it means to plug in when you know a formula for one variable in terms of another. It's just kind of counterintuitive that it's seemingly backwards. Well, anyway, that's how I want to view this, the substitution rule. I want to view this as that I have a function going, let's say this way, x is a function of t, and I want to view the substitution rule as saying if you have an expression, namely an integral, in terms of x, that you can pull that back. That effectively the substitution rule is allowing us to pull that back to rewrite as an integral in terms of t. Okay, so that's the first aspect of this that I want to point to. Now, this does a lot of the work for us. I mean, we've already talked about how this domain a to b on the t-axis turns into this domain from g of a to g of b on the x-axis. And we've already talked about that when you plug in, let's see here, when you plug in the function x equals g of t, you're literally just going to plug in everywhere you see an x on the right, you'll just put g of t on the left, whatever the formula for g of t is, just like on the example above. So there's one extra little thing that we need to talk about, and that is this g prime thing right here. What is the deal with the g prime? And again, there's different points of view, and this may or may not be what you saw in Calc 1, Calc 2. No problem. I want to take, though, this specific point of view as follows. dt I can draw on my picture as this. It represents the size, the width, if you will, of this little subinterval, and we think of this as a size. You might think of it as a distance. Now I want to tweak that a little bit. I now want to view dt as being a change, aka a vector. Just going to choose to view it that way. Right? That, I was at some value t, and then I'm going to imagine moving over to the right by some amount dt. Well, when you move over to the right in the t-axis, that's going to make the output values move over by some amount. And hopefully no surprise, the amount that the image moves in the target is not going to be the same as the amount that the input moved in the domain. Of course not. Input changes and output changes, right? Not necessarily the same. In fact, we've already got an established relationship between input changes and output changes. That's what the derivative does. The derivative is what I'm going to call the stretching factor. The derivative is what you multiply by input change to get output change, and so, as I'm interpreting it here, it's what you multiply by this size to give me this size. It's the factor by which output size is bigger than input size. Or you might say it as, it's the factor that this function stretches out little subintervals. The derivative says how much bigger they are when they come out than when they went in. What do you think? Everybody willing to buy it? Because it's just an interpretation, way I want to think about it. Of course, we already know from long ago that what the formula is. But as such, then, this dx, it's not dt. It's stretching factor times dt. Okay. All right. So, with all of that done, let's now ask, how would we extend this, viewed in this particular point of view? How would we extend this to a multivariable setting? And so here we go. Let's suppose we have a function with two input variables and outputs represented by another two output variables. All right. Instead of one in, one out, we have two in, two out. Well, I could imagine, hypothetically, if I had some domain over here in the UV space, and I'm going to pick a nice, pretty rectangle here, just because eventually it's going to be nice for this to be to have been chosen specifically as a nice domain. So, I'm drawing a rectangle. if I have a nice domain there on the left, I can ask, well, what comes out when I plug in all those points into this, whatever this function is? This is what we're eventually going to call our change of variables function. And what's going to come out is, well, some other domain, and probably not a nice, pretty convenient little rectangle. This change of variables function, who knows what it might be? It might curve, twist, bend, whatever, shear, rotate. There's lots of things that function could do. So we get a wacky, undesirable domain on the right. Okay. So all the same ideas in play if I have an integral on the right, and let's take a quick moment to recognize what a horror story this is, right? This weird domain on the right, the output domain you might call it. Curvy and cornery and stuff, right? If you slice this, depending on which way you slice it, in fact, as I have it drawn here, either way you slice it, you're going to be slicing through corners, and this is going to be a nightmare of an integral. So, pretty undesirable. Our goal is going to be then to figure out how we can pull back. I don't like this integral. I need to compute this integral for whatever reason, but I don't like it. I hate that domain. I want to figure out how I can rewrite this integral instead as an integral over this original, the original domain, or what I like to call the pullback domain. That's a much nicer integral. I mean, it's got a rectangular domain. When I write this as an iterated integral, the bounds are constants. Gotta love it. Okay, so that's the big idea. Does everybody see how this is analogous to substitutions? Yeah.
What are the S?
Oh yeah, I'll get there. Yeah, I haven't gotten to that yet. Yeah, details that I'm building up to. Okay, so this is our big picture strategy. How do we do it? Well, pretty much how we did it in the original single variable case. The function itself is telling us x and y as functions of u and v's. Oh, whoops, so hit the wrong button there, sorry. So plug that in. X and y are literally g of u comma v. So if we know this function, then I can just plug that in exactly as written, and that part's easy. The big question, the looming question, is what's the deal with the stretching factor, right? So we knew from previous experience what this stretching factor was in this single variable case. The stretching factor is just the derivative. So what I have to do now is figure out what is the relationship in this new context. What is the relationship between input little pieces of area, du dv, and output little pieces of area, dA? Right? If I'm going to, again, I keep in mind I'm rewriting, I'm starting with this integral on the right, I need to rewrite everything on the right over to the left, all in terms of u and v. How do I write this area in terms of u and v? Well, it will be some factor dU. So what is that factor? Now, there's a lot going on here. With as much as we have going on here, I don't want to get too bogged down in details, right? So for the moment, just so we can get the ball rolling, so we can get some examples done under our belt, get some in the win column, I'm just going to momentarily just tell you what this formula is, what that stretching factor is. And I'll justify this later. Probably won't be today. It'll probably be Monday. But here it is. This is the stretching factor. You take my word for it. It's the absolute value of the determinant of the Jacobian matrix, the derivative matrix for our change of variables function. Whatever that function is, whatever this g is, take the absolute value of the determinant of its derivative matrix. That's your stretching factor. Okay. Now, a couple of notational things. This is just stuff that has to get said. Quick reminder, don't forget that the derivative matrix itself is this formula right here. That's just a reminder from chapter 2, I guess it is. Right? Don't forget that the columns corresponding to taking partials with respect to certain input variables. The rows correspond to taking partials of certain output variables. All right. Now, this other little bit of notation I want to introduce, I think this is highly desirable for various reasons. This is a notation, kind of a shorthand, if you will, for the Jacobian determinant itself. It does not include the absolute values. You still got to say absolute values. This is just a shorthand for the Jacobian determinant. And you see what we have here, partial xy over partial uv. Now, why is that a reasonable notation? And there's various aspects to consider here. One is, notice that I'm taking, in this matrix, the partials of x and y. So, that's kind of what this, if you will, numerator says. It says partials of x and y, loosely speaking. And it's just notation. Arguably sloppy notation, but it's standard math slang, shorthand, convenient notation. Okay. Partials of x and y. And we're taking those partials with respect to u and v. And so again, this, what we have written in this, if you will, denominator, kind of suggestive that we're taking the partials with respect to u and v. So, it's not outrageous. It's terse and made up, but believable. Okay. Now here's something really nice about it, and this is one of the reasons that I really like this notation. If you were to take this formula, if you were to take this notation for the stretching factor and stick it into there, look what happens. Bear with me for a second. Let's see what happens here. I have partial xy, partial uv. There's that. Here, let me do it like this. That's what that is. I'm going to multiply, as written up here, by du dv. That's that. And let's see, what's that supposed to equal to? Well, altogether, that's supposed to equal to area in the xy plane, which I'm going to abbreviate as dx dy. And now here's where it gets kind of satisfying. And this is not a mathematical argument. This is notational suggestion. It's a memory trick, perhaps, right? This is not a mathematical thing, but you see this du dv and you see this partial uv, and there's this pretty strong urge to be like, oh, let's just cancel those, right? Now again, I the hairs on the back of my head stand up when I do that, because that's not a thing, right? I emphasize this thing that I've written like it's a denominator of a fraction. Don't forget, this is not a fraction, right? This is a determinant. It's not a fraction. This is just notation for a determinant. But we draw it as a fraction so that it'll look like a fraction, as a result of which then notice what we're left with is x's and y's, which looks like the dx dy that it's supposed to equal to. Isn't that nice? It's just notation. Right? This does not prove anything. This is just, you might think of it again as kind of a memory tool. If you find yourself at some point forgetting, oh gosh, well I've got this integral, and I know that the stretching factor, partial xy, partial uv, oh, is that the thing that I multiply by dx dy to get du dv? Or is it the thing I multiply by du dv to get dx dy? Surprisingly easy to kind of get confused at which way you go with it. Well, it goes the way that this suggestive at best, but honestly nonsensical faux cancellation would suggest that it goes. So, absolute nonsense, but it'll always lead you the right way. Is that okay? Yeah. Mm-hmm.
Would you like to summarize that?
Say it one more time.
Would you like to summarize that?
Can I summarize that?
Yeah.
I don't know what you mean.
So we're saying that if you plug in the partials of the reflect x and y over the partials reflecting the v,
Yeah.
and multiply that by du,
Uh-huh.
Like that's our stretching class.
Yeah, well, so right, what we already know, what is kind of the job of the stretching factor is to be a way to rewrite XY areas in terms of UV areas, right? Its job is to fit in this way, and so given that its job is to fit in that way, it's just somehow satisfying, and I emphasize at best, just satisfying. That it kind of looks like there's a sort of a faux cancellation, in which case it kind of, it's sort of suggestive of what it ought to be doing. That's all. So, please don't take this too seriously. This is not a real mathematical thing, but it is a handy kind of crutch / hack / memory tool for how to just keep yourself going the correct direction. That's all. Yeah. Okay. Alrighty, so with all of that noted, let's do an example. This is a highly manufactured example. Again, I don't want to get bogged down at the beginning of this discussion too much with the many distractions that will eventually present themselves. So for the moment, we're going to start off with an easy one where a lot of things are given that will not always be given. So in particular, we are given that we're starting off with the unit square in the UV plane. This is just given in the statement of the question. There's the unit square in the UV plane. And I'm given, furthermore, that the way x and y are functions of u and v, namely, what's going to eventually be my change of variables function, is this given function here. And then I'm further given that it is over the image of the square by that function, that is going to be the domain D for this integral that I want to compute. So kind of a weird way to phrase an integral, I suppose. But we're given the setup that I've got this as my domain, that this is the image, by way of a known function, of this square, also known and given. And so all of this context being given, the question I face is how to do this original integral. How am I going to compute the integral of x plus y over that ugly integral, ugly domain? How are we doing? Is everybody on board? All right. So now I want to recognize what a very difficult question this would be without change of variables. For a couple of reasons. First of all, as I slice, I'm going to hit that corner and this corner. And so, in fact, I really have kind of three separate integrals I'm going to need to compute here. If I were to just, dx dy or dy dx, whichever way you want to slice it, those corners are going to be in the way, and you're going to get three separate integrals to compute. Here's the second reason that I don't like this domain, and that is that let's just look at the curves themselves. Like, what's the equation for this edge? What's the relationship between x and y? I don't know. Right? I mean, here's x. X is this thing. Here's y. Y is that thing. What is the relationship between this and this? Also not clear, right? So I'd have I don't even know how hard that would be to figure out how I can find a relationship between x and y. That'd be a whole nother algebra problem. So this is a scary looking, very hard integral, as if I were to go straight at it. Okay. So let's then not go straight at it. Let's use change of variables. Change of variables, again, allows us to do a pullback. It allows us to take my undesirable domain over here, domain for the integral that I'm given, and to pull back and rewrite it as this integral computed over whatever this pullback domain is, the original domain, the one whose image is the later domain, which is a much nicer domain. It's a rectangle, for crying out loud. You gotta love it. Okay. So, that's the big plan. And in order to be able to do that, notice I am going to need to compute my stretching factor. I'll start by computing the Jacobian matrix, aka derivative matrix. There it is. That's just the various partials, right? So U partials, V partials of x and y. We take the determinant to get what we call the Jacobian determinant, and that works out to be 4uv minus 9. Now, importantly, I do need to take the absolute value of that thing. The absolute value is important. After all, let's go back up to here. What is the stretching factor in this story? Get this here. The stretching factor is a relationship between that green area, which is an intrinsically positive thing, and this blue area, which is itself also an area, also an intrinsically positive thing. So a factor relationship between two positive things has to be positive. Okay, so that absolute value is important. And here's where it gets a little annoying. How do I take an absolute value? Purple. How do I take an absolute value of some weirdo expression like 4uv minus 9? Problem. Everybody see where we're kind of stuck on this? Okay. Good news. The answer for how to deal with this, at least in this specific case, is actually on the screen right now looking at us. Here's the story. Don't forget, we already know our pullback domain. I already know that these are the only points I'm interested in, right here. This is my domain. That's where all of my U's and V's are going to be on that green rectangle. Okay, well, good news. That tells me that U specifically, right, there's the U axis. U is clearly always between 0 and 1. Right there in my picture. And then likewise, V, also on my picture, there's the V axis. V is also apparently always between 0 and 1. So now I can just eyeball this expression. UV is always less than 1. 4UV is always less than or equal to 4. And then I'm going to subtract 9. Guarantee that makes it negative. Okay, cool. Okay. It's always going to be different. Every expression, every pullback domain. So, I mean, you always have to tailor the argument appropriate to the context. But the way it works out in this case, the thing that I'm interested in taking the absolute value of is always negative. And good news. This thing, the thing that I'm taking the absolute value of is always negative, so its absolute value is the negative of that negative thing. And thus 9 minus 4uv. How are we doing? Okay. All right. Now, in theory, well, anyway, it's possible that we might not get the same happy answer every time. It worked out really great in this case that this was always negative. What if it's not? What if it were to end up that, there's some line like this and the expression in question that I need to take the absolute value of is positive up there and negative down here. What would I do there? Well, that would make this a much more annoying question because then I'd have to break up the pullback integral into two pieces. One up here where the absolute value of the expression is just the expression itself, because it's positive. And then a whole separate integral down here where the absolute value of the expression is the negative of that expression because the thing is negative. And so I'd have to treat each half separately, and I'd have two separate integrals. And this whole operation might just not be worth the trouble, and it certainly makes it a much harder problem. So anyway, I'm not planning that this will come up much, if at all. No promises, but that would certainly that would make this a much harder problem. Okay. All right. Well, we're in business now. It's just a matter of kind of plugging in. Let's see. Here we go. Our original integral that we wanted to compute. Here it is. on this horrifying domain. And let's see here, one bit at a time. What's x? Don't forget, the change of variables function is telling us both x and y in terms of u and v. So x, among other things, is looking at us right here. Why can I not get this stylus to work? X is just that. So just plug it right on in there. There's the formula for x. Write it down. Likewise, let's see here. Y. There's y here. Well, here's y. Y apparently is this function of u and v, and so we write it down right on in there. So all together then, our original integrand, x plus y, is just, well, this thing plus that thing. So that's the plugging in part of the story. That's the, if you will, this part of the story. Right? Turning the original integrand into other stuff. All in terms of u and v. Now, the only other thing we have to do is don't forget to stick in your stretching factor, and we're in business. So what is our stretching factor? Well, we just got through computing our stretching factor. Our stretching factor is that thing, and we've got ourselves a brand new integral. And before I clean it up and talk about how great this is, does everybody see the sort of the plugging in process and exactly what happened, how we implemented the formula there? Okay. All right, so how great is this? Well, first let me criticize it. This new integral that I'm so happy with, that integrand sure doesn't look very nice. Our integrand got a lot hairier. But it's still just a polynomial. It's not that bad, right? The big story here is not about the integrand. The big story is that a very unhappy domain that makes this a hard integral to deal with turned into, well, I'm now doing my new integral over the unit square, everybody's favorite domain for a two-dimensional integral, right? And that makes this a very desirable integral. I mean, sure, you got to multiply out a polynomial, no big deal. But then, as an iterated integral, 0 to 1, 0 to 1. Easy bounds, easy plugging in, no problem. So I'm going to call this a big win. That green integral is much easier than that blue integral. Everybody happy? Alrighty. All right. Now, again, that was a manufactured example, right? I mean, I rigged it up to where the output domain was exactly the. Not only is it the image of an input domain, but the input domain was given, and the function that turns the one into the other also given. Most of the time, that's not going to be the case. Most of the time, you're going to have to come up with your own change of variables function. So I'm going to talk through some examples real quick. Let me come back over here and remind you that we are talking, in fact, about a pullback. So whatever function you choose, right, we're going to be working backwards through that function, going from the right to the left. And so, in effect, what's going to happen to your domain is sort of the opposite of what the function does. So, for example, I claim that if your change of variables function adds the vector AB, the pullback, again, will do the opposite of that. It'll add the vector negative A, negative B. If your change of variables function stretches in one direction, the pullback will squish in that same direction by the same factor. And if your change of variables function is a counterclockwise rotation, then what's effectively going to happen to your domain is a clockwise rotation. And this is the one that I'm going to show you an example of on the next page. Here it is. So we've got here a given domain that is this square, defined by these 4 given corners. Here. Okay, y'all can think it through, persuade yourself that this is in fact a square. Okay. And we're going to compute an integral on that domain. And again, you look at this integral at a glance, you see this integrand, and you love that integrand, 2x minus y, nice and easy, lovely integrand. Again, usually not the issue. Having a nice integrand is not what we're worried about. What we're worried about is the domain. The domain is where corners come from, and thus what makes me have to break it up into separate pieces, and where I might have problems finding an equation for the bounding curve, and the domain is the scary part, right? So we don't really care about the fact that the integrand is nice. We're far more concerned about the fact that this is a unfortunate domain. In particular, look at those corners, and whichever way you slice, you're going to be slicing through two corners. So whichever way you slice, this is three separate iterated integrals. Everybody see why we don't like it? All right. So, okay. Well, here's what we're going to do. I'm going to observe. Now notice this, what I'm about to do, not in the statement of the question. The following is something I'm making up as part of the solution based on what I see in the problem. What I don't like about this square is that it's tilted, right? It's kind of been sort of rotated. Wouldn't it be nice if instead of that, wouldn't it be nice if I had kind of this, that yellow square, which just in order to get it out of the way, let me put it over here like this. Don't I like this S square much better? Right? Well, good news. This is easily related. The blue square is clearly a counterclockwise rotation. This transformation, T, that turns the pullback domain S into my actual unfortunate image domain D, is a counterclockwise rotation. Right? Well, when I then pull back, through that transformation, blue to yellow effectively is going to take that blue square and rotate it clockwise to become the yellow square. So again, change of variables functions counterclockwise. What that accomplishes is to turn my domain clockwise. Okay. So now there's some details in here that I'm going to kind of wave my hands at and remind y'all that this is all Math 218 right here. We've talked through some examples of this previously. I've noted several times previously that this kind of linear algebra is stuff that is going to come up significantly in this course. So just as a broad brushstrokes reminder. This function is a rotation. Rotations are linear transformations. All linear transformations can be represented by matrices. Matrices can be best understood by their columns, which are the images of the standard basis vectors. Right? So there's a bunch of little details in there, but that sort of sequence of connections allows you to take a simple task of, well, geometrically, let's just rotate the standard basis vectors. That'll give me my columns, which give me my matrix, which represents my rotation. And all together, the final punchline then for what this rotation is, our change of variables function is this right here. This is the relationship that turns u's and v's into x's and y's. If you don't feel comfortable with this process, come on into my office hours. I'll be very happy to walk you through it. But I want to make sure that everybody is good at this kind of linear algebra and geometric transformations of the plane in particular. Okay. Oh, and in 3-space. Likewise in 3-space. Okay, so I'm going to take that as all given. Okay, so with that done, we just need to start plugging and chugging. Jacobian determinant. Here's the Jacobian. We take the determinant. It's 1. How about that? Isn't that nice? And at a glance, it's tempting to look at that and be like, well, how could that be? Look at all the square roots and fractions and stuff. How did it all just perfectly cancel? We got 1 exactly? What are the odds? Well, in fact, I claim this is geometrically pretty plausible. Look, after all, at what our change of variables function is. It's just a rotation. When you rotate stuff, it doesn't change how big it is. Things stay the same size when you rotate them. So how much, by what factor do areas get stretched out when you rotate them? Well, not at all. They don't get bigger at all. Factor is 1. Should be 1, right? In other words, this is not an unexpected coincidence. This is exactly expected, because that's how rotations work. So now I think that's a worthy observation. That said, though, for Math 219 purposes, you do need to show me the calculation. My interest in this course is to make sure that you are proficient with computing Jacobian determinants to be stretching factors, etc. So do make sure to give me the actual calculation in Math 219. Now, that said, outside of Math 219, if you find yourself dealing with a rotation as change of basis matrix, boom, 1. It's your stretching factor. You just write it down, make the geometric case, done. Okay. In this course, I want to see the calculation. And we're off. Here's my stretching factor. Absolute value of 1, which of course is 1. That part was easy. Let's plug in. What do I do with this x right here? Well, don't forget x is part of what the change of variables function tells me. So it is this expression right there. Likewise, what is this y right here? Well, y is, again, part of what the change of variables function tells me, and it's this thing right there. So when you're doing the plugging in, note the change of variables function itself tells you exactly what to plug in for x and y, or whatever your variables might happen to be. Okay, so altogether then, the original integrand 2x minus y turns into, well, all of this, 2 times that thing minus that thing. We got our stretching factor inserted, and again, it's all over, and our new integral is found. This original integral that we didn't like, because again, the domain there is just horrible. I now have a new integral, and okay, fine, I'll concede that, yeah, these coefficients aren't integers anymore, right? But those are constants. It's really not that bad. It's still a linear polynomial. It's still a wonderfully simple integrand. But the big point, our domain is now just a square, so our iterated integral bounds are constants, and this is a big win. Much better integral. How we doing? Everybody's happy? Okay. All right. Okay. All right. A couple of details that I need to get said. Again, I don't like to get distracted too soon when there's so much else going on. But just to be clear, we do need our change of variables function to always be continuously differentiable. So we're only going to do stuff like rotations and other fairly simple change of variables. So no problem for the purposes of Math 219. Another subtlety that technically must be satisfied, but that we're not going to need to worry about in Math 219, is it has to be an invertible function. If your change of variables function is not invertible, then the following kind of weirdness can happen, just so you'll know what to be on the lookout for. You could have a non-invertible change of variables function that takes some input domain like this and turns it into an output domain, which is always a little bit of a challenge for me to draw. I'm going to do my best here. Something kind of like that. And so in some sense, what's happening here, all of this area it's getting kind of bent around and twisted around, but in such a way that it covers this area, and then as it goes around, it's going to come back and overlay on top of what it's already done, and effectively then double count whatever's in this area. And so, okay, you can't do, so you double counting would give you a wrong answer, and so, you can't allow any of this to happen either. So invertibility is a requirement to avoid this kind of problem. If you have if you have invertibility, then this will never happen. Okay. Everybody good? Okay, so now, real quick, going back to our initial setup. Your change of variables function goes to the right, pulling back goes to the left. Problem is that sometimes finding a change of variables function go in the direction that you need it to. And again, if I'm starting with a dx dy integral, and I want to be able to pull back that way, what if I can't find x and y as functions of u and v, thus getting my change of variables function going the way that it needs to go for this whole thing to work? What if the only function I can find is the opposite? What if I can find u and v as functions of x and y, but then I'm not pulling back, then I'm kind of pushing forward or something? Can you do that? Is that okay? In fact, it's going to present some problems, but ultimately it's kind of fine, because don't forget, this is in fact an equal sign, and equal signs work both ways. If A is equal to B, then B is equal to A. Equal signs go either way, it's fine, right? The problem is that we only know for the moment how to find stretching factors for functions that are going that way. So if we can figure out how to find stretching factors when they're going the other way, that'll work too. And we can totally set up our relationships between u and v and x and y, whichever direction happens to be convenient, and then, just deal with it appropriately. So that's going to be our next goal. That's what we're going to do here. And so let me just remind you, with a change of variables function going this way, the stretching factor for this function, we take the partials of the outputs, which are x and y, with respect to the inputs, u and v. There's our formula for stretching factor. Partials of the outputs with respect to the inputs. Jacobian determinant, all that. Okay. Now, let's set that aside. Let's kind of forget about all that. And let's imagine a scenario where I don't have that function, or don't want to for whatever reason. And what if my thing goes this way? Well, I can just write down, ignore the purple, and just say, all right, well, here's a change of variables function. What is my stretching factor for this dark blue change of variables function? Well, it's the partials of the outputs. Looking at the direction that the arrow is going, u and v are my outputs. So partials of my outputs with respect to my inputs. Now again, with the direction that the arrow is going, x and y are my inputs here. So I have partial uv over partial xy. Now there's a temptation to look at these two expressions, this and this, and instantly declare them as obviously reciprocals of each other. Because after all, look at them, they're fractions, and numerator, denominator, and that's how fractions work. But here's the thing, make sure to remember, these are not fractions. Right? We draw them as fractions because in one context that we've already observed, they kind of behave like fractions in a way. Not actually fractions. Each one of these is a determinant, not a fraction. So we cannot make an argument that hinges on them being fractions. There. But here's what we can do. We can say, well, altogether, if I have a little piece of area over here in the UV plane, and if I ask what happens all together when I push it forward, get some image over here in the XY plane, and then instantly come back to the UV plane, well, I'm going to get the exact same green area that I had in the first place because, well, we literally did nothing. We pushed it forward and came right back. Nothing happened. So altogether, the product of these stretching factors has to be 1. Because that's the factor by which you multiply by the green area to get the green area. Right? It didn't change. And having argued this, that this product is equal to 1, then we get this conclusion that, as we were kind of hoping, indeed, as their fraction notation would kind of suggest, these are reciprocals of each other. Not because they look like fractions, but we draw them to look like fractions because they're reciprocals of each other. Right? Does that make sense to everybody? So this is a conclusion, not a reason. Anyway. Okay, so that's going to be really useful, and I'm now aware. I just see that we've run out of time. So we're going to draw the line right here. We will pick up here on Monday. We'll see how useful this observation is for a really important example coming up on Monday. Y'all have